Okay, so it's 9 o'clock and time to start. So welcome all of you to this first session of the morning. The first speaker is Raul Monsalve, talking about recent progress by the mapper of the IgM spin temperature, MIST.
Okay, thank you very much. Hopefully you can hear me. Right, so first of all, I wanted to thank the organizers for the invitation and the opportunity to participate in this conference. Thank you very much. And unfortunately, I couldn't be there in person. It would have been really nice for me to do it, but it couldn't happen. So, but at least I will remotely give you an overview of our recent progress. So MIST is an experiment trying to detect the global 21 centimeter signal. And of course, ideally, we would want to go for the signal across the full spectrum, but it's in practice not possible, considering how difficult it is to detect this signal to begin with. And so we, for now, are optimizing our search across the range 25 to 105 megahertz, as you can see on this slide. This range primarily spans the frequency range where the cosmic dawn feature, absorption feature, is expected to be found, and also a little bit of the dark ages feature below 40 megahertz. MIST stands for Mapper of the IgM Spin Temperature, and this is an experiment that began in 2018. And here I show a summary of the institutions that participate in the experiment. Berkeley, McGill, Universidad Católica de la Santísima Concepción, UCSC from Chile, NRAO from the US, and also we have a collaborator from CSIRO, Nithya, actually, who should be among you these days. This experiment is funded primarily by the Chilean government as well as the Canadian government. Okay, so there are many philosophies when it comes to designing this type of experiment. Here I show two extreme cases. There are many, many other ways in which you can classify these experiments, and these are just two extremes to illustrate the approach that we have taken. So on the left, I'm indicating aspects that correspond to a design that is optimizing for signal to noise, meaning that one of the metrics that we are optimizing for is integration time. And to maximize the integration time, you would prefer to have a fixed installation and an instrument that is located at a single location from where you take a lot of data for a long time. In this case, you would be observing the sky through the same foregrounds, meaning foregrounds from the same latitude the whole time. Some approaches that people have taken when designing this type of instrument involve a large size with a lot of metal to simulate electromagnetically, primarily because of the ground plane designs. People have taken the approach of implement large ground planes, and there are good reasons for that. But when you do that, your electromagnetic simulations also become very large, and the computational expense grows with that. The geometry of these instruments, when including the metal ground planes, increases. It is more complex in general due to this ground plane. And typically in this type of design, people rely on cables for power, for communications, etc. So that is one possible design approach. A different approach is try to optimize for the understanding of systematics. In this way, you are not trying to get as much data as possible. You are testing different systematic effects and learning from that exploration. So here you can get away with a more portable design. And if it is portable, that means that you can take it to different sites and observe the sky from different latitudes. And that means observing through different foregrounds across 24 hours of right ascension. If these instruments are portable, that means that they are small and easier to simulate because there is less metal to simulate. Also, you can design these instruments to be simple geometrically, and especially if there is no metal ground plane involved. This has been the approach that in MIST we have taken. And in our design, we do not have any cables of any kind externally around the instrument. There are no cables connecting the antenna to the receiver and no cables leaving the receiver or providing power to the receiver or communications to the receiver of any kind. So the approach in MIST has been the one on the right-hand side. It is a small, simple, and portable instrument. We built two systems in 2022. These are total power radiometers spanning the frequency range that I mentioned before, 25 to 105 megahertz. So far, we have operated with horizontal blade dipole antennas without a ground plane. And in the field, we measure different quantities, but two of the most important ones are the sky spectra, of course, as well as the impedance of the antenna that we use for calibration. Again, these instruments are small and portable for deployment at remote locations. Their power consumption is 15 watts, and they are powered by 12-volt batteries. Here's a picture of one of the instruments. This is a picture taken in 2022 during our first observations in Nevada, in the Death Valley region. So here in this picture, the blue arrows indicate the horizontal blade dipole antenna, the receiver box under the antenna, and the fact that there is no metal ground plane in this design. This is a summary of papers that we have published on this instrument and effort. One paper summarizing the instrument design, another paper describing the sensitivity of the observations with this instrument to different soil characteristics in simulation. And the third paper, which we recently put on the archive about determining soil electrical properties using the antenna impedance. We will touch on this point in a few minutes. Okay, so since 2022, we have observed primarily at two locations in North America. One of them is the Nevada area and Eastern California, also in May 2022. The other place is near the McGill Arctic Research Station, or MARS, in the Canadian High Arctic. In the Arctic, we have observed in 2022, 2023, and 2024. And we are planning on doing observations again starting next week. I will be traveling to the Arctic again next week for to take observations this spring season. Okay, I will go over some of our efforts since 2022, hopefully quickly. Yeah, in 2022, we measured from Death Valley in Nevada. Then we went to the Arctic in July. And so this is how the Arctic looks in July. And these are McGill grad students, Ian Hendrickson and Vadim Vidula. They went with me. We were a team of 3 people, and we assembled the instrument there and took a further 10 days of data. Here is a summary of observations from the sites that we observed from in 2022. Deep Springs is in California, Death Valley in the middle is in Nevada, and the Arctic is on the right-hand side. And these waterfall plots show 19 hours of observation. The y-axis is time, and the x-axis is frequency from 25 to 105 megahertz. Hopefully, you can see the main details. The thing that I want to highlight is the RFI contamination in the FM range above 87 megahertz. You can see clearly that FM contamination in Deep Springs, in Death Valley, but there is nothing comparable in the Arctic. The main reason to go to the Arctic is due to its radio quiet characteristics. It is an extremely radio quiet site. So that applies not only in the FM range, but across the full spectrum, including in the HF range below 30 megahertz most of the time. Sometimes we do see HF RFI below 30 megahertz, or let's say between 15 and 30, but there are times when it's very quiet even in that part of the spectrum. Okay, this is another plot trying to get across the same point. This is a single spectrum at 41 second integration spectrum from Death Valley in Nevada, and you can see here encircled with this black line FM contamination from that location, and this is an equivalent plot for 41 second integration spectrum from Mars, from the Arctic. There is no visible RFI across our frequency range. Okay, in 2023, we went to the Arctic now in the spring. And this is how the Arctic looks in the spring. It looks more like the picture of what you have of the Arctic, completely white. And when we go there, we share the camp with other scientists. Most of them are glaciologists. And so here we are posing with them. And they are extremely nice people and knowledgeable of the Arctic, and we are extremely grateful to them. Without them, we wouldn't be able to do this experiment from the Arctic. Here is MIST taking observations in the Arctic in 2023. The soil during the spring consists of frozen soil and then a layer of snow on top of that. So MIST here is sitting on the snow. This is a picture of the trip that we did last year in 2024. It was a very similar trip. We were there with glaciologists and we had a great time. We went from mid-April to mid-May. And one of the differences between 2024 and 2023 is that last year we did observations with two instruments in parallel. So here is a picture of the first instrument, which is the standard MIST, meaning using the same antenna as before. And we observed with this instrument from the top of a frozen lake. The surface of the lake was frozen. The thickness of the ice was approximately 2 meters. And below the ice, the water is liquid water for like 25 meters. So this instrument was observing from that location. And also we observed with a second instrument, which we are calling MIST Low, which is an instrument with a larger antenna. And this instrument was located 8 kilometers southwest of the Mars camp and of the first instrument. They were separated by 8 kilometers. And with these two instruments, last year, we also took approximately 10 days of data. Our instruments are not temperature controlled, in particular the electronics. And because of that, we need to do a receiver calibration at the temperatures at which we do the sky observations. So we do this in the Arctic itself. When we are there, we calibrate the electronics. And this is a picture of one of those calibration efforts, which we did at minus 30 degrees Celsius. Yeah, and as I said before, we are planning to go again to the Arctic next week for another month of Arctic adventures. So to summarize these Arctic efforts, we have gathered approximately 30 days of observations from the Arctic between 2022 and 2024, which is sufficient to test the presence of the edge signal in terms of signal-to-noise ratio. But we are working very hard on trying to understand all the systematic effects in our observations and focusing on soil effects. We don't observe with a metal ground plane, and that there are some advantages to that, but the disadvantage is that we are very sensitive to the electrical parameters of the soil. Here is a summary of the configurations and conditions of the observations over the last 3 years. Yeah, it's a summary of what I said before. The soils on which we observe have been different. Other aspects that have been different between observations is that we have used different receivers with different instruments. We have 2 receivers, and we have used different receivers at different times and with different antennas. So, and in addition to that, we have observed with the antenna at different orientations, sometimes orientated north-south, one time we did observations with the antenna orientated east-west. So we are spanning an interesting range of configurations and conditions, and we are exploring all this data to learn about our systematic effects with these observations. As I said before, one of the main effects that we need to understand are soil effects, and one of the ways in which these effects manifest is in how they affect the beam, the fraction of the beam that points toward the sky. And that fraction, first of all, is frequency dependent. And second, it will vary depending on the electrical properties of the soil. Okay, so I'm trying to get across that point with these 2 plots. On the left, you see simulations of the beam efficiency, which is the fraction of the beam above the soil. And that fraction changes depending on what assumptions you make for the soil in terms of its electrical conductivity and relative permittivity. Okay, and it can vary by a lot, by tens of %. Okay, now on the left, the assumptions that we made are that the soil is uniform. In reality, unfortunately, the soil will not be uniform. We need to try to find the most uniform soil and observe from there, but in general, the soil will not be uniform. So on the right, what we simulated is cases in which the bottom layer changes with respect to the top layer. It is a 2-layer model on the right. And when we have situations like that, there will be ripples that will appear in the beam efficiency, in the fraction of the beam that points toward the sky. So we need to know what shape this quantity has in frequency. And to know that, we need to know the electrical parameters of the soil. So one technique that we are testing to understand these parameters is using the impedance of the antenna that we use for sky observations. We need to measure this impedance no matter what, because we need it for receiver calibration. So since we are already measuring this impedance, the question is, can we use this impedance also to characterize the soil? And this is a technique that we have been testing for a couple of years already. In this figure, what I'm showing is the resistance and reactance of the same antenna. So resistance is the top panel, reactance is the bottom panel, but at different sites. And so different colors represent different sites. And as you can see, the impedance will change depending on the site and primarily due to the different electrical properties of those sites. So the question is, can we solve this inverse problem going from impedance to soil parameters? And we recently, like a couple of weeks ago, we put this paper on the archive describing a proof of concept where we try to determine soil electrical parameters from the antenna impedance. And here are our preliminary results. In the top row, the solid line curves represent measurements at 3 sites, and the dashed lines represent simulations, electromagnetic simulations of the impedance that we have fitted to the real data. And from those fits, we have determined soil electrical parameters, which are the numbers in blue in the top row. The bottom row shows residuals for the fits between models and data. So we are obtaining interesting uncertainties, relatively low uncertainties that are promising for our application of determining the beam of the instrument pointing toward the sky. Okay. Now, again, this paper was a proof of concept. We have a second paper describing a soil characterization effort coming out soon, with much better results. So please stay tuned and keep an eye out for that. Using the antenna impedance is not the only way in which we are trying to characterize the soil. We have also been using and learning about a ground penetrating radar, or GPR, and also other techniques like using separate antennas designed specifically for soil characterization, which we insert into the soil or into the snow or whatever the soil is at a given time. So pictures of that are on the right-hand side here. Okay, so in summary, MIST has gathered approximately 30 days of observations from the Arctic between 2022 and 2024, which is sufficient to test the presence of the edge signal. So far, the Arctic observations are spanning an interesting range of instrumental configurations and observation conditions. And we are working hard on understanding the systematic effects, especially the soil effects. Thank you very much.
Any questions?
Raul, it's very exciting to see.
Thank you.
I'll be here, but I understand if you're going off to the Arctic next week.
Right. Yes.
So I had one very small, easy question and one other question. So the first one is your sort of standard dipole and your MIST low. Do they overlap? I guess they overlap sort of during the cosmic dawn in frequency, so that if you make a detection, right, or find something, that you will find it with both instruments. I guess that's the idea, right?
Yes, that's the idea. But also the idea is that with MIST low, with the larger antenna, we have a slightly better efficiency at lower frequencies, even below 25 megahertz. And so we were eager to explore as low as possible last year, and that's why we implemented that antenna. And the plan for this year is to do the same, observe with the larger antenna and with the standard antenna.
Thanks. And the other question is, it's very nice to see that you're sort of probing these soil properties, and of course, right, you'll see quite significant effects if you have multiple layers. But I was just also wondering about the spatial differences, right? I mean, this soil is not just going to be uniform slabs below your instrument. There will be spatial changes as well, which make it far more complicated. So have you thought about that, or is that a negligible effect?
We have thought about that a lot, and in fact, we optimize our site selection for homogeneity, and or if they are not fully homogeneous, and if they are better characterized in terms of vertical layers or a vertical stratification, hopefully they are uniform horizontally as much as possible, each layer. And actually in the Arctic, it is the conditions are kind of favorable in that regard, because in the summer, the soil in the Arctic can be described in terms of an unfrozen layer on top, which is called the active layer, and then permafrost underneath, which is frozen soil. And so that is a clear differentiation between these two layers with properties that are well studied and relatively uniform. And for instance, last year we measured also on the frozen lake that the top 2 meters of the lake are ice, and below that it's just water. So again, those are good conditions. I mean, as good as it gets when it comes to modeling a 2-layer soil. So, well, I could give you more examples, but we are trying to optimize for that.
Okay, thank you. Thank you.
Thank you.
Any other questions?
Hi, nice talk.
Thank
I
you.
assume you're doing a Dickey switching for the calibration. So my question was, because the entire band may not be the best to calibrate, are you doing a joint fitting for these sub-bands for the calibration?
I am not sure I understand your question. What do you mean by the entire band might not be?
So, so some part of the band, as you showed, was like full of RFIs, and so what I'm assuming is that the entire band may not be the best to calibrate with a single, let's say, method. So, do you take chunks of like or sub bands and then you join fit each of these bands, maybe overlapping bands, to achieve the entire calibration for the entire band?
Well, we apply many layers of calibration. One of those layers is receiver calibration. And for that type of calibration, we don't need antenna measurements. So the measurements that we use are very clean because they are not done with an antenna. So we can do receiver calibration across a wide band for in all cases. So I guess your question doesn't apply to that. So I'm a little confused about what it really applies to. I'm not sure. I mean, there is RFI in the antenna measurements, but we try to clean that the best we can in other ways, but we don't consider that a calibration step.
All right, thanks.
Any final questions? If not, then let's thank the speaker again.
Thank you very much.